Um, experimental results on the shock loading of different materials obtained by Professor Meshcherikov from St. Petersburg Institute of Engineering Problems have shown that shock loading, dynamic process initiated by shock loading have special features that differ them from the quasi-static loading. For example, dynamic processes induced by shock loading are followed by a whole complex of multi-stage and multi-scale relaxation processes and energy exchange that can lead under some boundary conditions to self-organization of new internal structures of the medium. Retarding and collective responses of the medium reaction to the short loading can lead to multi-velocity pulsations, oscillation, and in the results to instability of the whole system. All these processes demonstrate the strong dependence on the strain rate, and that is why in many cases the conventional continuum mechanics cannot explain all these effects because, first of all, because of the new structures that self-organization and self-organization that occurs during and after these processes. So it is necessary to apply such a new approach over the limits of the classical continuum mechanics. And first of all, I would to say about the results obtained in non-equilibrium statistical mechanics. Some decades ago, Professor Zubarev from Moscow Mathematical Institute, from the first principles, has deduced non-local relationships with memory between thermodynamic fluxes and forces valid far from equilibrium. These relationships, fluxes and forces, this is gradients of macroscopic fields, are integral all over the volume of the system and depend on the history of the loading process. These relationships contain as an integral kernel spatio-temporal correlation functions, which present functionals, non-linear functionals of all the history of the process, in all the system, in all volume of the system. This correlation function in general case are unknown, and this circumstance was an obstacle for a long time for using these results in practical problems. But on the base of these statistical mechanical results, a new approach was developed in St. Petersburg State University, and this approach allows a construction of flexible mathematical models of correlation function in these relationships that depend on some parameters having physical sense and connected to the sizes of new internal structures arising inside the material during the loading and after the loading. In this approach, these non-local relationships with memory are used with this model correlation functions, depending on the parameters S. And in case when these parameters have a sense of radius correlation, spatial radius correlation, for example. And if this radius correlation tends to 0, we have usual linear relationship between flux and forces, just in classical results of linear thermodynamics of reversible processes. But when the correlations embrace all the system, we have, from these relationships, we have usual elastic reaction of the medium to the loading. And for a long time, when correlation decay, we have classical hydrodynamic medium reaction. And here we can see that really for the first stage, for small typical times of the process, we have elastic reaction when stress, for example, is proportional to the deformation. And for long typical times, the last stage of the relaxation process gives us the hydrodynamical relationships like a Newtonian model of fluids between stress and strain rate. And during dynamical processes, we have the we have the intermediate case between the two limiting situations, between elastic reaction and hydrodynamic reaction. In this case, the medium reacts like a multi-phase medium with a complicated and changing during the process internal structure. Such a model can close the mass, the general transport equations under conditions far from equilibrium. So, as we can, using this approach, describe such transition regimes, we apply this method to this model, to the problem of the shock-induced elastoplastic wave evolution under the plane loading conditions. We have chosen the model parameters that connected, in this case, to the changing structure of our system. And this, excuse me. We have typical relaxation time, retardation time, the loading time, which is never taken into consideration for conventional problems connected to the shock wave. Their ratio gives us these model parameters that, under conditions close to experiments, what we are going to describe, can evaluate. And these evaluations are presented here. Under these evaluations of our parameters connected to the experimental conditions, we can take a new reference connected to the elastic precursor for the wave here, and to move together with the elastic precursor, which is moving at the constant sound velocity, longitudinal sound velocity, and this evaluation allows us to separate quick and slow variables. Quick variables describe the waveform itself, and slow its evolution. Then the experimental conditions allow us to linearize mass and momentum transport equations in the new reference here, and to close them using non-local equation. Here we take into account only temporal correlations, because the first stage, non-local spatial correlation, we can neglect under the given experimental conditions. And all this allow us to get essential simplification of the whole problems, and to reduce it to the only one integral equation for the mass velocity. Where is the mass velocity? An approximate solution have been obtained for the constant strain rate during the shock, and for the first equation 7 gives us for during the continuum loading for short typical times usual elastic model and hydrodynamic, and equation 8 gives us after effects which play an important role and connected to the rise time of the plastic front, which is forming as an initial effect. The equation 7 was applied to the problem of the plane loading that was obtained by Wood. He have got this formula under the assumption above. And our model gives us a possibility to describe the intermediate region, transition between elastic and plastic branches of stress-strain diagram, depending with yield limit on strain rate, essentially dependent, and that is why we can say so that for high strain rate loading, these results are incorrect. Then, in order to get the concrete values of the model parameters having the sense about, we can use we can use adaptive control theory via feedback, and to choose the goal function and the control parameters. Goal function is the entropy generation all over the system, which reach its maximum in thermodynamic equilibrium, and the speed gradient method gives a shortest way to reach the goal, and gives us, for the control parameter which are connected, it's our parameters of the model, and these equations are, describe system evolution with macroscopic progresses. And the last one, here is the comparison with the experimental results. Here we can see that all experimental points in a wide range of the shock of the impact velocity are on the plane of the model parameters, lay in the strain lines different for different materials. And for the surface of the entropy generation rate given in the speed gradient method gives a trajectory which projection is entirely coincide with these experimental ones. Conclusions, you can see that non-local model developing non-local transport theory are appropriate to describe both continual medium reaction and transition regime with structure effects. And internal control is necessary to complete the non-local model and to govern the system evolution with the changing internal structure. A goal I have already told, and the evolution trajectories are valid for description of the structure evolution of the system.
Okay. Thank you very much for your presentation.